Hi, welcome back to Calculus. Today we're looking at section 4.8, antiderivatives. So the definition of an antiderivative is that a function capital F is an antiderivative of the function little f on an interval I if capital F prime of x is equal to little f of x for all x in that interval. Basically, you have an antiderivative if, when you take its derivative, you get the original function. So we're doing derivatives backwards now, and this is going to be kind of fun. Couple of notes here. Well, one real note here to begin with. Traditionally, we use capital letters for our antiderivatives. It's just a kind of way of saying, hey, it's just a way of keeping things straight. So that's, and also tying the f's together because they are connected, right? Once the function, once the antiderivative, they are connected together. So we like having that same letter, but we're going to use capital letters for the antiderivative. So I have a pretty straightforward example here of finding an antiderivative. At this point, we're going to do a lot of kind of guessing and checking to try and find our way through, but I also have some suggestions, and we're going to start with a polynomial, and polynomials, it turns out, they're really nice, which is great. So here's my function, f of x is equal to 6x to the fifth plus 3x to the fourth. So I want to find its antiderivative, and hopefully you can see this. I have a couple blanks in front of my x's because I want to figure out what to do with those coefficients. But the exponents are pretty nice, right? We know that when we take a derivative of a polynomial, the exponents go down by 1. So it stands to reason that if we take an antiderivative, the exponents are going to go up by 1. So my 5 becomes a 6, and my 4 becomes a 5. Now, about those coefficients. The first term is pretty easy to see because guess what? If we think about this antiderivative, what would have to happen when you took its derivative? Remember, this derivative should equal the original function. Well, the 6 would drop down front. So there is really no need for a coefficient here. I'll go ahead and put a 1 there just for kicks. But another way to think of that is that 6 divided by that new exponent of 6 gives us 1. Right, when we take a derivative, we bring the exponent down and multiply. To go backwards, we're going to divide those coefficients by the new exponent. So here we can see the second half of the polynomial. We have 3x to the fourth. When you raise its power by 1, you get a 5. 3 is not a 5, so these are not the same thing. But guess what? What we just said still applies. When we took the derivative, if we were to go backwards and take this derivative, the 5 would have to come down and get multiplied. Well, 5 times what is 3? That's pretty nicely just 3/5. But again, notice that that's just 3 divided by the 5. So anytime you're working with polynomials and you have to take an antiderivative, just raise the power by 1 and divide the leading coefficient by that higher power. And there you go. There's your antiderivative for this particular example. All right, so let's keep going. This will be fun. Okay, so continuing on, I have here now a theorem that we're going to look at. That's also going to be super important to us. Theorem 8, out of your book, says if capital F is an antiderivative of little f, then the most general antiderivative of little f is capital F of x plus c, where c is an arbitrary constant. So I'm going to refer you back. Once upon a time, we kind of did this just a little bit before. But basically, you can add a constant onto any function, and it doesn't change its derivative, because the derivative of a constant is always 0. So in this case, if you take this derivative, the c goes away, and you get f prime of x would still just be that little f. So adding that constant doesn't change where we're at. And so this is what's called the most general antiderivative because it offers a whole family of functions that will have the exact same derivative. And so most of the time when we say find the general antiderivative of something, what we mean is you better put that c on it, this arbitrary constant. What is c? Who knows? It's arbitrary. So as an example, find an antiderivative of f of x equal to 4x cubed. This satisfies capital F of 1 is equal to 6. So here we have a set of conditions that we want to work for capital F. So we take its antiderivative. We know, okay, my power is going to go up by 1. 4 divided by 4 just gives me 1, so I just have x to the 4th. But there's my c, my arbitrary constant. Then using the information that we were given, we plug in the 1. We get 1 to the 4th plus c, and that has to equal to 6. And solving it, you get c is 5. So the antiderivative that we want is capital F of x is equal to x to the 4th plus 5. All right, let's get some more on the board. Okay, so continuing on, I want to point out that in your book, on page 267, there is a list of general antiderivatives. So anytime you're having trouble coming up with one, go to page 267, and that'll at least maybe help point you in the right direction. All right, but I want to do 2 more examples, and then we'll do a little physics, and I don't know, conclude with some more good stuff. So I want to find the general antiderivative here for 2 different functions, f of x here, and then in a minute g of x. So my f of x is the sine of 2x. We need an antiderivative. What we know, but there's a lot going on with this little problem. First of all, we know that the derivative of cosine is negative sine. So if I'm going to go backwards, I'm going to need a negative and a cosine. Okay, so you can see I have the negative, the cosine, and I have that 2x. But unfortunately, we also have a chain rule involved here. We have that 2 times the x inside of my sine. And if we think about when we get back here, you have a 2 times the x inside of that cosine, which means when you took the derivative from capital F to little f, thinking, going as the derivative in the derivative direction, you'd have to do a chain rule and multiply by 2. So 2 times a half would get us the no with the coefficient of 1. Basically, since we have a number on the inside, it's a chain rule problem. To get it back to the antiderivative that we want, we're just going to divide by that number. So I multiply by a half because that's the same thing. So the negative comes about because that way my negative cosine will turn into a sine. And yeah, there we go with my plus c on the end. That one's kind of fun and tricky, so spend some time looking at that one. My next one, little g of x is 2 to the x. So again, we have an exponential problem here, and we know its derivative. So we're trying to go backwards, but we do know we do know the derivative of 2 to the x. Remember, when you have 2 to the x, its derivative is just natural log of 2 times 2 to the x. Well, there's no natural log of 2 here. That means we need to divide our capital G of x by the natural log of 2, or in other words, multiply by 1 over the natural log of 2. That way, when we take this derivative, the 2 to the x will give us a natural log of 2 that, when multiplied by this, will make it go away. So there's a lot of division going on when we take these antiderivatives. And of course, don't forget that capital C. All right, let's get another board. We have more good things to talk about. All right, so next up, we have some antiderivative rules. We have 3 of them we're going to need to look at: constant multiples, a negative rule, and sums and differences. These are all the really nice ones. These all work exactly like, I don't know, at least exactly like I think they should, and probably like you would like them to as well. So what happens, constant multiples? So let's say you have something multiplied by a more basic function. For the antiderivative, you just keep that something times the antiderivative, and then still plus our arbitrary constant. Notice we don't need to multiply the arbitrary constant by whatever k is, because c is already arbitrary. Multiplying it by k just leaves it k times arbitrary, which is still arbitrary. For the negatives, if you have a negative in front of your function, you just get a negative in front of your antiderivative, still plus c. And sums or differences, this is a good one because it does allow us to take antiderivatives of the pieces separately, which is going to be good for a lot of problems. So if you have f of x plus or minus g of x, you get capital F of x plus or minus g of x plus c. Again, you don't need 2 arbitrary constants here for the same reason we didn't need to multiply up there. If you add 2 arbitrary numbers together, you still have an arbitrary number. So you only need the one antiderivative, or the one c to go along with this. All right, let's do some physics.